Okay, so we have a very simplistic model here. I'll try and zoom in for those of you that can't see in the back. But we have a model of a solid part, and you can see that the material here, I'll see if I can zoom in a little bit. Customize. Okay, so hopefully you can see that a little better now that I've made my icons larger. Okay, so we have a model of a spring, and we have these these orange caps on the bottom and the top. And this is just to facilitate our ability to apply a load to this on a flat surface, okay? So all we want to do is see what the spring constant of this is, given the fact that this is the geometry, okay? Don't concern yourself too much with the physical dimensions of it, but it's a helical geometry like you'd expect. And we've defined a simple material here that's just alloy steel. So if you right click on this, I've already set this kind of up for you, but if you go to edit material, it will allow you to, it'll bring up the entire SolidWorks library of materials, and under the steel subfolder, we can scroll down and see alloy steel, which is just the most generic version of steel that you can see here. All of the properties are defined, and we have nothing here that's defined in nonlinear properties, so this is not the viscoelastic version that your colleague there was suggesting. Not that you would have a viscoelastic steel, but anyways, so we can click apply, and the simple part is kind of done. This is the CAD geometry we started with. And now we want to go to the tab here that says SolidWorks add-ins, and you can click SolidWorks simulation if you don't already have the simulation tab on the bottom here. So this is what's going to execute your ability to create a new study. And this new study is just the language to determine or to create an analysis model. So when you click on the drop down here, you can click new study. So everyone should be able to get to this point. You can call it whatever you like, but now you can see you're confronted with all of those different options of the different domains of studies that you can do or analysis models. So static, frequency, topology, thermal, buckling, fatigue, nonlinear, a bunch of different ones. We want to just do a simple static one, so we will click that little icon right there. And if we want to use a 3D simplification, if it's a simple 2D model, we can do that. If we want to do 3D, we'll just leave it as such. So we can click the checkbox here, and now it'll bring us to another tab here that's called Static 2. I've already solved this in the background, but Static 2 now is showing up on the bottom of our page. And our model, which is our CAD, if we click back here, it's going to bring up everything in the history tree on the left that's defining the CAD geometry. Once we click on Static 2, now it's going to bring up everything that's inside of our analysis model. So you can see here we have the actual CAD, which is called spring alloy steel. Okay, then we have all of the different ingredients that create the analysis model: the connections, the boundary conditions for the fixtures, the loading, the mesh, and then whatever results options we configure. Okay, so the first thing that we want to do is just look at some of the buttons up here, because we know that we need to mesh the part. We know that we need to apply boundary conditions, but we can see, okay, fixtures advisor is how we apply some boundary conditions as in the form of fixtures. So just to kind of expedite the process here, very simply, we want to apply a fixed geometry on the bottom of this. Okay, so pretty simple. And we just select the face. The moment we do that, it brings up this dialog box on the left, and it's going to ask us, well, what kind of geometry you want, roller, slider, fixed hinge, or fixed geometry, and then you need to select the geometry. So we can click OK, and the moment we do that, you'll see that now it's populated another item here under our fixtures. Pretty simple. The other thing that we want to do is add a load. So that's under external load advisor, and you can see here when we select the drop down, we can apply a force, a torque, a pressure, a gravitational force, centrifugal force, bearing loads, many different options here. Okay, you can even do flow effects, temperature, but we just want a simple force. And we now are confronted with the question, well, what force do we want? We know we want to apply it up here because we just want to compress the spring, okay? And you can see by accident I've had two faces selected. If I click on one of them, I can check which one it is, okay? I didn't deselect the face from my previous selection, so I'll right-click on that and click delete. Okay, so I want to apply a force. Here's the geometry that's defining where the force is being applied, and then I want to select the unit system, so I can do metric or imperial. I want SI units, and I want to apply, let's say, 10 newtons of force. Okay, and in this case, the vector is highlighting the direction of the force. If I want to reverse it and pull up instead of push down, I can do that by clicking this checkbox. So all of this is pretty simple. Now you can see I have a fixed constraint, I have a force, and now you need to ask yourself, is this enough to physically constrain this part? What else do I need to do? So think about if you took your thumb on the spring, okay, what would happen? In the idealistic scenario, who's ever done that with a spring that couldn't fall? What could happen? It could buckle, slam across the room. So maybe we should worry about that, but let's just try in this case and deal with it like this. But we could apply another fixture and we can say, okay, well, maybe we want to constrain the top to moving only in the vertical direction. We don't want any lateral movement. And why would there be lateral movement in the first place? If we orient our view here, the indexing of this top and bottom part of the spring means that the start and finish of this is slightly different, so the spring force might not be perfectly aligned. Okay, when all these coils start to compress, there might be some lateral movement of this. So we need to worry about that when we do this. And I'll check my solve version of the model, and you can see that I've actually applied a separate constraint here, okay, saying on cylindrical faces, meaning that it's a cylindrical constraint that's forcing that to move only in the vertical direction. So I'll jump back to the model that I haven't solved yet. I just click X here. So I'll jump back to the tab where you guys are working along with here, and I can say fixture, and I want to apply maybe a fixed geometry, and I want to say apply to this face, and maybe it can be a roller, meaning it can move up and down like such. Okay, we could also hinge it if we wanted, but this particular geometry doesn't call for that. Okay, so we can do a roller slider. There's a bunch of options to do this here, and we now have our material defined, we have our CAD geometry defined, and we have our forces and navigations defined. The only thing we have to do is create a mesh. So if we go to the screen here, we right click, there's an option here to create a mesh. Okay, and this is where I get a little bit sad inside because it's a simple slider bar. Okay, some of the models that we saw in the beginning months, if not like years to create, because the mesh was so late, it to do it properly. This is using an auto mesh technique where it's going to discretize the geometry automatically for you. You could just leave it in the middle just to start out with, and but you can control the mesh density however you like. The density of the mesh kind of dictates how many individual calculation points there will be. So if you have very let's say sharp geometry that you want to properly resolve, that's a good place to refine the mesh. You can just globally refine it by dragging this to coarse versus fine. Finer meshes will have higher density, coarser meshes will have less density, but you can also define a minimum mesh size here. So let's say we wanted to have more than a few elements across this spring here. So we could say, okay, well, the diameter of the spring is a millimeter or whatever it is. We want to have at least 5 elements, and you can set that here if you'd like. So we'll just click OK and let the auto mesh do its thing. It's going to bring up a dialog box in a second here. Hopefully. Let's try again. Maybe I clicked the wrong button. Okay, so now run. Here we go. Mesh controls. What did we do? Create mesh. The create mesh, and it should do this. Sorry, it's because I clicked the wrong OK button. But you should get a dialog box that says the meshing is in progress. Kind of freezes everything for you while it's happening. Is there anybody that's having issues with? Probably not everyone's following along because this is pretty easy so far. So it's going in the background, it's looking at all the surfaces that are there, it's discretizing the geometry, and maybe in this case, in live in the lecture, probably makes sense to make it a coarser mesh, just because if it takes this long to mesh, it's probably going to take a lot longer to solve. So we'll see what happens here in a second. I think it took, on the coarse setting, it took like 5 seconds to mesh, so it's almost an order of magnitude longer now. If you click K2 and you go and run, you can see, okay, well, I want to create a mesh, and I want it to be as coarse as possible. Ideally, if you had time and you didn't want to do the slide, you can do the default setting for that, and then understand where you need to refine or coarsen from there. But we'll see how this kind of works here. My computer's really needing a cup of coffee this morning. So we'll let that load in the background, and I'll keep going through the PowerPoint here as that's loading. Where were we? So the objective here is to find what the spring constant is. So the force is 0.1. And we can calculate that from there. And you can get a nice animation in the end of it. Do something like that. The second exercise is this cantilever L bracket, where we're applying a fixed boundary condition at the top, and we're going to apply a force at the end. So I think the SolidWorks model is also contained within the file there. And you can see that we're going to change the fillet configuration depending on this root of the bending, depending on, and visualize the changes in the stress. So I think now the meshing is done. So this is what it came up with automatically with the coarse mesh. So probably a really good starting point. And now we have our mesh, we have our boundary conditions, we have our loads, our fixtures, and we have our material model. So we can just interrogate the mesh a little bit, and you can see all these little triangular elements that are here. It's pretty well representing the geometry, at least right now. Okay, and it's automatically selected that minimum mesh size based on how small the geometry is in certain locations. So now to run the actual simulation, there is a hotkey button up here that says run the study. You can also just right click on the study here in the history tree and click run here. And it's going to warn me that I have load this space again. That's fine. Would you continue to run the study? Let's see. I have less than 500 megabytes. So it'll